Welcome to lecture number 11 in the course Advanced Robotics Applications. Now, in the last class, we talked about the basics of linear control systems, where I discussed about position regulators, partition controllers, and now you have a fair idea of how a control system is actually designed. How do you tune the gains, for example, KP, KD, to get a response of a system. Okay, so today we'll start off with the next part, that is experimentation. Now, with the last few lectures, you have a background of understanding what is forward kinematics, inverse kinematics, then trajectory planning, and some basics of control systems. And from today, we'll move on to the next part, that is experimentation. Now, in experimentation, we'll move on first to robot programming. That is, industrial robots are programmed in a language like VAL language. What does this language look like? And then towards the end of the course, we'll move on to actual writing a program and controlling an industrial robot. Now, after today's class on VAL programming language, we'll move on to microcontrollers. That is, how can you use a microcontroller for building very simple experimental robotic systems. Okay, so today we'll move on to robot programming. That is, when you're using an industrial robot, you're supposed to program the robot using a language, and this language is basically called VAL. So how do we program an industrial robot using a VAL language? Now, we have seen that a robot, whatever you have studied so far, you would understand that a robot would essentially consist of, so if you have a link here, okay, so this is a link, and at every joint we have a motor, there is an encoder at the back, and there's a gear in front. And what you have seen is that this total system is controlled by a PC or a microcontroller. Okay, so this total system consists of different subsystems. For example, there is the mechanical hardware, which is the arms or the links. Okay, then we have the motion transmission. There can be gears. Then there is a gripper in the front. So this consists of the mechanical hardware part of the robot. Now, there is also the robot control unit, which consists of the robot controller, which can be a PC or can be a microcontroller. And there are motor, sensors, power amplifiers, then ADCs and DSCs. Now, apart from this, the robot controller and the mechanical hardware, the robot will not be working alone. So the robot is normally going to interface with other machines. For example, there is a pick and place parts carousel somewhere. So the robot has to pick up a part coming on a conveyor and place it somewhere on a machine. Or maybe after machining is done, it can take the part and put it for inspection. So the robot is also going to be interfaced with other machines, okay, with which it is working. So there has to be a central controller which is going to do the interfacing and do the scheduling. So basically there are three subsystems. One is the mechanical hardware, that is this one. The second is the robot control unit, which is actually controlling. So there is this the closed loop control system. So it is taking the sensory feedback, it is getting the desired position and doing the closed loop control. And for various interfacing with sensors and encoders, it can have ADCs, DSCs. For driving motors, it can have power amplifiers. So this is the second part. So one system is this, second system is that, and the third subsystem is this one, which is the central controller for interfacing robot with other machines. Okay. Now, you can program a robot. When I mean a robot here, I basically mean an industrial robot. So an industrial robot which is used for pot welding, spray painting, or pick and place or assembly in industries. So such robots can be programmed by using a teach pendant. Now, teach pendant is something which is like the remote control in your television. So you have seen the remote controls in the televisions. So in the case of the robot, the remote control looks something similar. So there are joint numbers. So that is my 1, 2, 3, 4, 5. And there is plus, minus, which are toggle keys. So if you want to move joint number 1, you simply press that and move it towards the plus side. The joint will move in the clockwise direction. Okay. So using the teach pendant, you can manually teach a robot. You can teach basically different points. And these points are recorded in the memory of the robot. And then you can play back. So if I have a robot here, I can use the teach pendant and take the end effector from one point to another point. And when it is moving in space, I can move each of the joints manually and independently. And when it is moving in space, I can record the end effector positions. And then later I can play back and say play back along this. So by this, for example, you can pick and place an object. Suppose there is an object here. I can pick it up. Okay, so I can pick up an object and then take and place the object somewhere else. Okay, so this is essentially a manual method. The other method is by using a computer program. and that is basically a program-based control, in which case we write a computer program, and when you execute the computer program, the desired task is performed. For example, again, suppose you want to move the end effector through these points. Let me call this P1, P2, P3. So we program the coordinates of these points in space, and then I can say that fit a trajectory or move along these points and go from point A to point B. Okay, so this is how a computer program is executed. So we'll be seeing both of them. Now, historically speaking, robot programming languages can be divided into three groups. The first is the first generation language. This is very early, about 1970s or 1960s. The first robots were using the first generation languages, and these are basically for very simple commands like pick and place applications, and they had very limited interaction with the outside world. What I mean, the environment. So these robots were essentially for pick and place. They could pick up an object, put it somewhere. They did not have interaction with the environment. That means you could not have computer vision or force torque sensors on these robots. Okay. Now the second generation robots is somewhere around 1980s. Now these robots basically have better interaction with the environment. That means you can have force sensors, touch sensors, ADCs, DSCs, computer vision can be integrated with them. Okay. So suppose a part is coming on a conveyor. In a second generation language, you could use the computer vision system to actually identify that the part is coming, and when the part has reached the location, it can tell the robot to go and pick it up. Okay, so these are second generation languages. What is the difference between the first generation and second generation? It is essentially interaction with the environment. Okay, now the third generation languages are basically what we call intelligent languages, and these are languages which have the ability to understand general commands. For example, if you say pick up an object A, suppose there is an object on a table here, and you say pick up this object on a table, it should be able to understand, compute what is the coordinate of that of the object, go and catch it, and then go and put it somewhere else. Okay, so these are more like general language, ability to understand general language commands. Okay, now we are still here, the year 2000 and beyond, we are still here because the biggest challenge here is to be able to interpret language. You can say something, but you can mean something else. And that's where language interpretation is very, very difficult actually. And that is where actually a lot of people are doing research into how to go from a higher level language that is used by humans to a lower level language which is understood by machines. Okay, so these are essentially the three generations of languages. Now, in terms of languages, there has been the earliest language. There are a couple of different types of languages which were available. One was VAL, which is called Victor's Assembly Language. Now, this is the earliest language, 1960s, and this was developed for the Unimation, for the Puma robot, for the Unimation by the Unimation company. So, in our in one of our experiments, we will also do experiments using the Puma robot, and we had studied about the inverse kinematics of the Puma, which is a 6 degree of freedom industrial robot. Okay, so this VAL language was developed for the Puma robot, 1960. This was basically VAL 1. After that, we have VAL 2. So we'll be studying VAL 2. Now, VAL 2 has more interaction with the environment. So you can interface sensors with it. You can put different kinds of algorithms on it. Okay. So this is the earliest language. Now, 95% robots use the VAL language. Of industrial robots today use VAL language. Now, the other language that was developed by IBM. So at IBM used to make robots a long time ago. And this was developed by IBM for manufacturing automation systems. Okay. And the language they developed was called AML. Today, IBM does not make robots anymore, so this language is not there anymore. The third is RPL. Again, 1960s. This language was developed basically based on the Fortran language. Okay. Now you know that there are different languages. BASIC is there, Fortran is there, C is there. So the basis of RPL language is Fortran. And today, RPL is also not used because the company is not there anymore. Okay, so these two are not there, and only VAL language is there, and the basis of VAL language is something like BASIC language. Okay, so the VAL language is based on the BASIC language. What I mean is that you might have studied basic language programming in school. Okay, so the way a basic language is written is that you have a line number, say example, and then you have a command. For example, A plus B. Okay, then you have the next line number, maybe 20, which is equal to C is equal to A plus C is equal to A plus C, just for example. Okay, something like this. So the basic language is written this way, and the structure of the VAL language is exactly similar to the basic language. Now, a VAL language program will be studying VAL 2. And after studying, we'll also be programming an industrial robot to perform a task using VAL2. Now, the VAL language is divided into these four parts, or the whole VAL program rather. So this VAL program is divided into four parts. The first part consists of the constants, variables, and data objects. Okay. Now, what are constants? For example, we are using the word pi. So pi is equal to 3.14. That's a constant. Okay. Suppose we say variable a is equal to 10. I define this as a constant. Then that variable a always remains as 10. So you can have constants, you can have variables. Now, variables, as the name indicates, are variables that can take different values. Okay. Then you can have data objects, like in C language, you have objects and classes. It's almost a similar structure. So the first thing in a VAL program is you need to define the constants, variables, and data objects. The second is the motion command, motion control commands. Now, a robot moves in space. Okay, so a robot moves in space. So when it is moving from one point to another point, these are what we call as motion commands, motion control commands. So from P1 go to P2, that's a motion control command. Okay, so move P1, move P2. Now, robot hand control. Now, robot also has a hand or a gripper. Okay, so robot hand control basically would mean that either you open the gripper or you close the gripper. Okay, so open, close. Okay. Third is program control and input output control. That is basically interfacing. So this is interfacing with external sensors, and then used for communication. Okay, so either you're interfacing with different kind of sensors, or you're basically communicating with other machines or other sensors. Okay, so a VAL program will consist of these four parts: constants, variables, data objects, motion control commands, robot hand control, and program control, input output control. Now, the first is variables, constants, data objects, that you understand what it means. The second part is motion control commands. Now, variables can be points, and variable can have a variable name. For example, this P1 is a variable name. And in this case, we are saying that a P1 is a point, and the point has coordinates x, y, and z, and alpha, beta, gamma is the roll, pitch, yaw angles at the wrist. So this is roll, pitch, and yaw angles at the wrist. Okay, so at the wrist. Okay, so x, y, z are the coordinates of the wrist point, and alpha, beta, gamma are the roll, pitch, yaw at the wrist. So this point P1, which is defined as P1, has coordinates this and that is the angle of the wrist. Now, motion. So this is how we are defining a point in space. Next is the motion control commands. So if you say move P1, it basically move to the point P1. Now the P1 has been defined here already. Okay, so P1 has coordinates x, y, z, alpha, beta, gamma. So when we say move P1, it'll move to the point P1. Number two is moves P1. Now this S basically means move in a straight line. Okay, so when you say moves S1, it moves in a straight line. Okay, so the difference between a move and a moves is that this moves using the shortest path, whereas this one moves in a straight line. Now, why would you need two commands? That's why would you need move and moves? You could do with only one command. That's an interesting question. Suppose you are at the point P1 and you want to go to the point P2. Okay, let me say I'm at P1 and I want to go to the point P2. So that's my point P2. Okay, now if I say move P1, which trajectory will it take? So it has to find the distance. It has to go to the point P2. Now it can go like this, 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 it can go from here, it can go from there are infinite ways. Which one will it take? Okay. Now, if you just think a little bit, the trajectory should be energy optimal, right? So it should go in such a way that the energy requirement is minimum. Okay. So how would you? Which trajectory would take the minimum energy? Now, the trajectory that would take the minimum energy need not be a straight line. Generally, it is not a straight line. Why? So you can get the minimum energy trajectory by simply minimizing the joint motion. So what we call the minimum angle norm, which means that the minimum joints will move. Okay, So the minimum joints will move, which will give you the minimum energy. So this will ensure that energy is minimum. Okay, and this will not be a straight line. So this will, something to remember here is that not normally a straight line. Okay, so which trajectory will it take to go from here to here? It will take a trajectory which is going to move the least number of joints. So if it can move only this joint and come from here to here, then it will move only this joint and it will consume the least energy. Okay, and that is how the robot would move from one point to another point, maybe like this. Okay, now if you say moves, then it has to move in a straight line. Now why is that moves command required? For example, if you are picking up an object, so I have kept an object here on the table and my gripper is positioned like this. Okay, now I want to go to the point P1 here. Now if I say go to the point P1, again it is going to do minimum energy norm. Okay, it is going to move with a trajectory which is going to be minimum energy. So it need not be a straight line. So it can come from here also, or it can try and go from here also, depending on whichever is the minimum energy trajectory. And if it starts going from the bottom, then it can become dangerous, right? So this minimum, if you simply say move P1, it will try and go to the point P1 using the minimum energy, and that trajectory need not be a straight line. But in this case, we want a straight line. So we are going to say moves. If I say moves P1, then this is going to move in a straight line and come down, and it will come here and then catch it and go back. Okay. Now, why don't you always use moves command then? Then maybe what is the point in having move? You can always use moves. Now, moves, if you think about a straight line motion, the straight line consists of infinite points. Okay, so at every point, it has to do inverse kinematics and find the solution. So first of all, this moves command, first of all, it is slow, okay, because it has to do inverse kinematics for a very large number of points. Number two is that it consumes more energy. Okay, because of which we have these two commands, move and moves. Okay, so normally when it's just moving in space, we say move, but when it is picking up an object, then we specifically say S or move S or moves, such that the trajectory is always in a straight line. I hope you understand why you need two commands now. Okay, now let's look at draw is basically an incremental command. So this is incremental. That means it makes a correction, incremental or correction command. That is, if you have reached a point P1 and you want to still move in the del X, del Y, and del Z directions, basically you're giving the small amounts by which it is moving. Okay. Then approach P1. Now when we are catching an object, unlike human beings, the robot will always go on top and stand like that. Okay, this is my point P1. So when I'm saying approach P1, so it is going and standing on top of P1 and keeping a distance of 50 in the Z direction. This is my Z direction. Okay. So before catching an object, we normally say approach P1. So it is approaching the point P1 and keeping the axis like this, okay, facing downwards along this Z axis, and the distance is 50 from there. Okay. So before you catch an object, we always say approach P1. So this is for catching an object. Now depart P1. So if you're after catching, if you're going up, then we say depart P1. So it is going backward and keeping a distance of 50 in the Z direction. So approach and depart are essentially for catching and then going up. Okay. Now robot hand control commands. We have hand control, that is basically the gripper control. So the gripper control commands are basically open and close. Okay, open as the name indicates will open the finger, close as the name indicates will close the finger. Okay. So there is open and close. But we also have open eye and close eye. Now let's look at this very interesting example here. So we have an object on a table and this is a gripper which is kept there. Okay, so this is my point P1. Okay. Now suppose I say move to the point P1, move, or I say approach P1. Approach P1 and keep a distance of 100. Maybe I say this my distance is 100. Okay, so approach P1 and keep a distance of 100. Now if I say moves P1, it will come down straight like that. Okay, and I say open. So let me put line numbers 20, 30. Then I say 30, 40. move P1, then I say close, then I say 50 is depart P1, okay, keeping a distance of 200. Okay, now suppose I write this program. Now how the program would operate is the compiler is going to compile it line by line. So first it is going to catch the first line, and it is going to say approach P1 and keep a distance of 100. So basically it will come here and position itself like this, keep a distance of 100. Then it says open. So suppose the gripper was closed. Suppose in this position the gripper was closed position. Okay. Then it says open. So it will start opening. Now when it is opening, the program has already moved to the third line, which says moves P1. So when it is opening, the gripper is already starting to move. If you can imagine what I'm saying, if you understand what I'm saying. So this open command, open for opening the gripper, takes some time. Okay. So this open command, because the gripper has to open, and most of the grippers are probably pneumatic, or it acts by air pressure. So when it is given air pressure, what would happen is the gripper will slowly start opening, and it will take some time to open. Okay. Now when the gripper is opening, it has already moved to the third line, which says moves P1. So as the gripper is opening, it has already moved down, and if it moves very quickly down, what can happen is it can go and hit this object because it is not fully open. Okay. So before the gripper moves, we should ensure that it is fully opened. I hope you understand this very important point, that before the gripper moves, it should be fully open. Okay. So before the gripper starts moving in this line, it should be fully open, and that is where we use our closed loop command, which is called open I. So open I basically means open immediate. Okay, open immediate basically means that it will open, and only after it has fully opened, then it will move to the next line. Okay, it will execute the next line. So this is an interesting command again. Now again, you can ask the same question, that why not have only have open I and close I? Okay, why have another one open and close? Now the same logic applies, is that open I is a closed loop command. It takes more time. Okay, so what will happen is it will slow down the program. Now in robotics applications, it's very, very important that we perform in the fastest possible way. Why? Because even a very small delay somewhere, because the robot is going to have millions of cycles. Okay, a robot works 24 hours a day for 365 days in 2 years. So a robot would be working for maybe millions of cycles. So if there is a small delay in any cycle, it adds up to a very large delay at the end. Okay, and that is the reason why when you're not picking up an object, for example, the robot is just moving, say another example where the end effector is just moving from this point to that point in free space. So this is free space, then end effector is just moving. Okay, there is no object or anything. In that case, you can use open. Okay, so open is a faster command. So the robot is opening the gripper and it is also moving. Now it is safe because there is no object there. Whereas in the case of picking up an object, then we have to be careful to use open I or close I always. Okay. Okay. Now other commands we can see. Number one are called the speed control. So basically what we see in terms of our program details, the VAL language program essentially consists of these 4 parts. There are variables, there are data objects. Then there is the motion control command, which is basically the move command, move and moves, 2 commands. Okay, so move to the point and moves to the point. Robot hand control can be open and close. Okay, or open I and close I. And then there is program input output control that I'm coming to now. Okay, so what we see here is that the hand control commands has basically open I, close I when you're picking up an object, and you can simply use open and close when you're not picking up an object. Okay, the other commands that are used, number one is speed. To control the speeds is 60 inches per second. You can also have meters per second. So MPS, meters per second. This means 60 inches per second or 60 meters per second. You can define a path between 3 points A1, A2, A3. Suppose there are 3 points A1, A2, and A3. Then basically it will define a path, means it will form a trajectory between these 3 points. Then we can have pause or delay. So this basically means the delay or pause in milliseconds. So suppose I say delay 100, it means delay 100 milliseconds or wait there for 100 milliseconds. Now, these are some basic applications of robotics that we'll be looking at. Number one is a robot can pick up an object from a conveyor. Say, for example, this is a conveyor which is moving. Parts are coming, work parts are coming on the conveyor. The robot has to pick up a part and then put it into a box here. This is what we call by indexing. Okay. So now suppose the conveyor is moving and the part is coming. So there has to be some kind of sensor which will detect that the part has come to the desired location from where the robot has to pick it up. Okay, so there has to be some kind of sensor. So when the part comes, the sensor will tell the conveyor to stop. The conveyor will stop, and then tell the robot that the part has come. Now the robot will pick it up, and then will also inform the conveyor that I have now picked it up. So the conveyor tells the robot to pick up, and the robot will tell after picking up, the robot will tell the conveyor that it is picked up. Okay, and then the first part it is going to take and put it here, second one here, third one here, fourth one here, then fifth, sixth, seventh, eighth, like that. Okay, which is basically indexing. So something that we see here is that for a robot to do a task, it has to be interfaced with some sensor. For example, in this case, there is a conveyor and it is interfaced with a conveyor, and it has to also interface means it has to communicate. So number one, there is interfacing, and number two is there is communication. Okay, so communication means the robot has to communicate with the conveyor has to communicate with the robot or with other machines. So there has to be some way of communication, there has to be some way of interfacing with sensors. Okay, otherwise the robot will not be able to perform any task. So this would mean that the robot must have some way of communicating and getting some sensor input output onto itself or its own controller. This is another example. There is a part coming in a conveyor. There is maybe there is a sensor here. So on the top, let's say there is a sensor here, which is detecting that the part has come. After the part has come, the sensor will tell the conveyor to stop. The conveyor will tell the robot that the part has come. The robot will go and catch this part and go and maybe put it onto this. After it picks up, it will tell the conveyor that I have picked up, you start again. So this all means that there is some kind of communication. Okay. Now the robot may need to put it into an empty machine. So the machines must also be able to tell the robot whether it is empty or not. So maybe 1 means full, 0 means empty. So these are all communication ways by which the robot can communicate with the machines, or the machines communicate with the robot. Okay. So the simplest way of communication is by means of on-off sensors. So we'll be doing all these experiments using microcontrollers. So what is the simplest way a microcontroller or a controller can communicate with a sensor or with another machine? So it is simply by using on-off signals. Now we have studied different kind of sensors like ultrasonic sensors, Hall effect, conductive sensors, and also limit switches. So the robot can communicate by sending on or off signals. Okay. Now on basically means that the particular channel or the particular wire in that is high. So I can simply say that this is a conveyor and the part is coming on the conveyor. There's a part which is here and there is a sensor which is checking if a part has come. Okay. And there is a robot here which has to go and pick it up. So this is my robot. Okay. Now when the sensor detects that the part has come, it can simply become high. So what would happen is this will be connected to the conveyor and it can also be connected to the robot. Okay, this is a, you can consider this to be a wire. We say it's a particular channel is connected to 1 here, 2 here, some channel number. We'll do the details of it when we come to the experiments part, but this is just an example that this is a wire, and the moment the sensor detects that a part has come, it can make that wire high, which means it can send 5 volts on this wire. The moment the robot receives this 5 volts, it essentially understands that the part has come. Okay, and it can also make this one high such that the conveyor understands part has come, so it should stop. Next, the robot will go and pick it up. Okay, so after the robot picks up, it has to tell the conveyor again. So there could be another wire which is connected there. It makes this one high. Okay, so either it can be 0 and 5 volts. 0 means part is not there or it's a false condition. 5 volts or 1, so it basically can communicate by 1 or 0 volts or 5 volts. Okay, so this is a wire which is connecting these different machines and the sensor, and it can simply make that it can give a voltage of 5 volts on that wire. and whatever machine is receiving it, it understands that it's high now. So whatever logic has been used, it will execute that logic. Okay, so at the smallest level or the lowest level, machines can communicate by giving 5 volt or by making it 0 volt. Okay, that's how microcontrollers also communicate. Okay, so in terms of 1 and 0, in terms of ladder logic, it can be 1 and 0. 1 can be true and 0 can be false. So 5 volt means true, some condition has happened, and 0 volt means false, some condition is not true. Okay, so this is the smallest level. Now, for a robot to operate, there must also be some logical statements. For example, the statement go to line number 20. So when the program is executing, it says go to line number 20. So this is line number. Okay, then go sub and return. So these are sub programs, and every sub program is followed with a return. Okay, then we can have if then else. So if condition is satisfied, then do this, else do something else. Then pause, proceed. Now this is another the same type of communication, which the syntax is signal. For example, signal or sig stands for signal. Now this means channel number 2. So this one means channel number 2. So this is channel number 2 is plus, and this one means channel number 3. Number 3 is minus. So plus can means plus 5 volts, and this can 0 can means 0 volt. Okay, so if sig 2 3, then do this, else wait. Okay, or the second statement, if you see wait sig minus 1 2, this means channel number 1 should become minus or 0, and channel number 2 should become plus or plus 5 volts. Okay, so this is how the program is written, or the syntax for communication using channels is written. Now reset turns off all the external channels. We can simply say on 2 off 3 also. So on 2 will make channel number 2 plus, and off 3 will make channel number 3 minus. Then we can have reset. So this is the most fundamental or the basic way by which robots can communicate with other systems. Okay. Now something to note here is that at the basic level, it is only 5 volts and 0 volts, or 1 and 0. It's only 1 or 0. That means true or false. There is only 2 states of that logic. There is nothing more than that. But a robot would also need, especially VAL2, would also need to interface with other kind of sensors. And sensors, as you know, could be analog sensors. For example, a thermocouple temperature sensor. A temperature sensor like a thermocouple. Could be a analog sensor. Okay. Then you could have a digital sensor like an encoder. So an encoder is a digital sensor. It gives a 1010 signal. Okay. Then you can have counters. Then you can have other kind of sensors. Okay. So a robot would need to interface with all of this kind of. For example, analog sensor. Suppose it is measuring force, or torque, or moment acting at a joint. Then this force is a continuous reading, right? It's not binary. So there should be some way by which it should be able to convert this force reading, which is analog, to digital. Now, what is the difference between digital and analog? So essentially what we see is that, okay, before I proceed there. So taking these external sensors, which are continuous with respect to time, you need to have a data acquisition system which is going to take this as an input and then process it and then give it to the robot controller. Okay, now this is basically called a data acquisition hardware. So what is data acquisition? The process by which phenomena in the real world can be translated and manipulated by computer readable signals. And that is basically what a data acquisition system does. Okay, the physical phenomena could be force, it could be temperature in a room, it could be pressure inside a chamber, etc. Now, the other term we used is analog and digital. Now, analog signals are continuous signals with respect to time. So this is continuous with respect to time. Okay, this means that if you're measuring, for example, temperature in a thermocouple, so what it is measuring is the voltage, or a strain gauge, which is measuring voltage. So this is a continuous signal. So if I draw it with respect to time, so this is my voltage, the signal could be something like this. With respect to time, it is continuous. Okay, or if I take a force signal, so a force coming with respect to time somewhere, it could be it would be a continuous signal. Okay, whereas a digital signal is essentially this continuous signal is broken up or sampled at a particular frequency, and only those parts are recorded and kept. Why? Because a computer is a digital device. it cannot read analog signals straight away. Okay, so there has to be some way by which you need to convert also. So there are two kinds of signals. One is a digital analog signal like this. Now if I do the conversion of this only at those points, then what is going to happen is that I will end up with a signal which is something like this. Okay, so only at those points I have sampled, and hence that is my signal now. Of course you can reconstruct and do all that. So this is an analog signal, this is a digital signal corresponding. Okay, so the sensor signals that are coming could be analog, could be digital. For example, analog, as I gave the example, is the temperature sensor is analog, force sensor is analog. Okay, digital could be encoder, or counter could be digital, it's just giving 1010. Now a digital signal is essentially discrete with respect to so an analog signal is sampled at particular frequencies, and this results in a digital signal. Okay, so a digital signal has values only at certain instance of time. For example, this is the state of a digital signal. Now a computer or a microcontroller cannot read analog signals. Okay, so we need to convert analog signals to digital signals. Why? Because as you know that a computer is basically a digital device, so it can read in terms of zeros and ones, but it cannot read continuous signals with respect to time. So whatever continuous signal is there or analog signal is there, it needs to be converted into a digital signal, and then the computer can store it and read it. Okay, so such could be temperature, force signal. This should need to be converted to digital signals for a computer to read. This is one which is basically called analog to digital converter, or an ADC. Now you can also have a DSC in which you're converting a digital signal to an analog signal. For example, digital signal needs to be converted to drive a motor, for example. Okay, so you may need to convert from a digital to an analog to drive a particular device, okay, or actuate a particular device. So robots normally have ADCs and they have DSCs also. Microcontrollers normally have ADCs. Okay, can normally have ADCs. Now, what is the syntax? The syntax is very, very simple. The syntax for ADC and DSC is ADC1. So ADC1 would mean ADC on channel number 1 is connected to sensor number 1. For example, this is a temperature sensor, for example. Okay, that means I'm defining that ADC channel number 1 is the temperature sensor. Then I can say that variable 1 is ADC1. Okay, so whatever value is coming for the temperature sensor on sensor number 1, that sensor is this ADC is going to convert that from an analog to a digital signal, and is going to assign it to variable number 1. Okay, I hope you understand the syntax. Similarly, here DSC1 is a constant, and DSC1 is equal to 3 plus constant. So here DSC1 means DSC channel number 1. Channel number 1, this is channel number 1. Okay, so this is the syntax of using ADCs and DSCs. Now there can be other also functions that are used, for example sine, cos, square root. So this is sine A, square root, not equal, equal, greater than. So these are all computations, operations that are allowed. Okay. Now, as I said in the beginning of the class today, that we can program a robot using a teach pendant, or you can program it based on the program-based control. So the desired task in the case of program-based control, like val2, we just talked about val2. So you write this as a sequence of motions in a language such as val2, and these motions are then played back and carried out, executed one at a time. Okay. Now there is another way of programming which is very often called lead-through teaching. Now lead-through teaching is for basically teaching skills, which are very skills difficult to program. So with what we have explained in class today, it basically you get the idea that when you're writing a robot program, then basically it is about points in space, P1, P2, P3. You're defining these points in space, and then it is moving through those points. Okay. But for cases where it is difficult to define points in space, now if you're wondering what is that, for example in welding. Okay, so when you're welding, for example, this is a weld being made. Okay, so this is a weld which is being made. Okay, so how is the weld made? There is a consumable electrode which is coming in there, and this consumable electrode has a a plasma arc which is coming in there, and the expert welder moves the arc and moves it, what we call weaves the weld, and then forms the weld. Now in terms of the welding electrode, consumable electrode, there is a plasma arc which is coming, so the electrode has to be moved down because it is getting consumed. So this electrode is consumed and hence it has to move down a little bit. It has to keep moving down as it is getting consumed, plus it has to be moved. Okay, so it is extremely difficult to actually define the points in such cases. For example, what is the rate at which it should be moved down? What is the rate at which this should be weaving like this or moving in that way? Okay, what are the exact coordinates? That would be difficult. Okay. So in such cases, we can do a lead through teaching. So on one side, you see an expert welder and he is carrying a joystick. So this is basically a joystick. Okay, and he performs the same motion as that of welding on the actual part. And when he is moving, the coordinates of the joystick tip is getting recorded in the computer. Okay, and these points are then played back onto the robot. So the robot is performing exactly the same kind of motion. Okay, so lead through teaching essentially means that for skills which are difficult to program, for example, welding is one. Welding is one, assembly is the other one. It's very difficult to assemble parts because again it is difficult to define points in space for assembly because there will always be error. And if there is very small error also, there will be jamming of the parts. Okay, so in such cases, we can teach the skills of the human operator to that of a robot in this way. Now let's look at a very simple program. Now the program for this, we also have a similar program in our Puma robot programming and Swire robot programming when we come to that a few classes later. So this is a Puma robot. So this is basically a Puma robot which has 6 degrees of freedom. So we need not worry about all that. The robot program doesn't consider things like degrees of freedom and all that, how many, what is the structure and all. Inverse kinematics, forward kinematics is taken care of by the robot controller. So the robot program essentially has to do with points in space. Which are the points through which you want to move the end effector? So let's look at this case, this example. The objective here is to pick up one part from the pallet. So this is a pallet which is there and these are parts which are kept on the pallet. Now if I see the top view, then the top view is here. Okay, so this is the top view. These are the parts which are kept, and these are the dimensions. So the distance from here to here is 20, here to here is 30, here is 20, then is 50, 50. So the parts are kept on this pallet in this configuration. Okay. Now the objective is to pick up one part one at a time. Maybe catch the first one. Okay, catch the first one, pick it up, and then put it in this queue, drop it there, and then take the second one, drop it in here. Keep doing that. Okay, how many parts are there? If you look at the indexing, there are 3 rows and 4 columns. Okay, so there are 3 rows and 4 columns on this pallet. Okay, so there are many ways of writing a program. There is a good way of writing a program and a bad way of writing a program. Okay, as you know that writing programs can be written in many different ways. So a bad way of writing the program would be that catch this part, drop it here, then go to this part, catch it, drop it here, then go to this part, catch it, drop it here, go to this part, catch it, drop it here. Okay, and you have so many lines going on. A good way of writing a program would be that the main task, what is the main task? Main task is to pick and drop. This is the main task. Okay, so pick a part from the pallet. Pick from where? Pick from the pallet, and drop where? Drop at the queue. Okay, so basically the main task would be to pick up a part from here and drop it there, and these parts are basically kept in an indexed way. Okay, so we can have a subprogram which is going to index from where it is going to pick up. Okay, so first I pick up the first one, then I shift it there, then I shift it there, then I shift it there. So the subprogram can do that shifting or indexing. So subprogram can do the indexing. Okay, and the main program has only one line, which is pick up from here and drop it there. That's a good way of writing a program. Okay, now the advantage of that also would be that if there is any change in these rows and columns here, suppose now I want a system in which there are 5 rows and 6 columns, then all I need to do is just change that number. Everything else works the same. Okay, so this is what the program looks like. First is we need to define the points in space, and I define this corner point. The corner of the palette is known, so I know the XYZ of that corner point. Okay, that is taught, that has to be taught. Then what it does is it first moves the corner to the top of this, the first object. Then it catches the first object and then takes it, and this is the first object, takes it and drops it there. Then it goes to the subprogram and indexes, means it changes the corner point from here to there now, or we can call it the pick point, to here to here. Then it catches this, drops it there, and goes back again. Okay. Third is it again indexes here, goes there and goes back again. Okay. So what it is doing first, this is my main program, or I can call this the main program. In the main program, the task is to simply pick up and drop, and in the subprogram, the task is to index. Okay, so basically what it will do is it is going to index that pickup point each time. Okay, so this is how the program looks like. So the program name is called program palette. Okay, so we can call this the program palette. And if we say remark is corner and the qt locations are taught. So obviously we must know what is the coordinates of this point here, the corner point, and what is the qt location also we must know. The coordinates of the qt we should know. Okay. Okay, so the program starts off with first saying that max column is equal to 4 and the max row is equal to 3. So it defines how many rows and how many columns are there. The next is it defines from which column and which row you're going to start. So it says that start from row number 1 and column number 1. Okay, so it starts from row number 1, column number 1. Then it defines pick. The point is going to pick as the corner point which has been taught already. Okay. Then it says shift pick by 20 minus 20, 60. Let's go there and what it means. Let's understand. So we are defining the corner point as pick. So this is my pick point. Okay. So pick is equal to corner and corner has been taught the coordinates. Then I'm shifting this pick point to the top of this point. So I'm moving in this direction by 20 minus 20 and 60 on top of the object. Okay, that is this command 20 minus 20, 60. Then I say open eye. Please note this open eye. Okay, that means open immediate. Then it moves to the point pick. So it moves to the point pick means it goes on top of this object here now. This is the pick point now. So it goes to the top of the pick point here now. Okay, then what does it do? Then it draw. You can either say draw, you can say moves. Okay, moves. You need to define the moves point. Okay, so they have not defined the moves point. So what they have done intelligently, if you just know the pick point, you don't need to define the object where it is going to catch. So you simply draw. This is x, y, and z. So in the z direction, it moves by minus 25. Okay, so this is my 60. If this is my object. Okay, and if this is my 60, so it was here, like that. That's 60. So what it does, it just comes to minus 25 down. So the object, this is here now. Okay, so without defining this point P1 and saying move to that point or moves to this point, it is simply saying draw, which is an incremental command 0, 0, minus 25. So it's coming down. Then you say close eye. Okay, close eye means close immediate. Then draw 0, 0, 25. So go up by 25 now. Okay, then move to the point qt, which is already defined. Open eye, drop it. Okay, so it has picked up the first object, gone to the qt, dropped it. Then go sub palette. It goes to go sub means go sub program palette. Okay, so the go sub program to the palette is this program. So from here it comes here. Now in the palette go sub palette program, this is basically for indexing. So what it does is it sets column is equal to column plus 1. So the way it is going to operate is first it will pick up this one, then it will index to this one, then it will index to this one, then index to this one. And after indexing from here to here, or changing the corner point from here to here, it will check whether you have exceeded the total number of columns or not. Because if you have exceeded, that means you need to come to the next row now. Okay. So what it does here is it sets the column to the next column. So column plus 1. We have started with column equal to 4. We started with column equal to 1. Okay. And so it goes to column number 1, which is equal to 2. Now then it checks if column is greater than max column. Max column is 4. Max column is 4. So if it is greater than 4, that means you have exceeded your total columns. Then you should go to the next row. So what it does, it increments the row to row plus 1. Okay. So basically from here to here, here to here, then it checks and then comes here, then like this, then here, okay. Now in our case, in the first case, it is not exceeded, so it will shift pick by 50 0 0. So if you see 50 0 0, what it is this is 50, this distance is 50, so from here it goes 50 0 0, okay. So it has shifted the pick point by 50 0 0, then go to 10. This is my point 10, it goes to the point 10. Again, move pick, draw, catch it, and drop it in the queue and come back to the subprogram. Okay, so it comes back to the subprogram and keeps doing this. Now, the moment the number of columns have been exceeded, it increments the row to row plus 1. Okay, and and also checks if the total number of rows have been exceeded. If both the rows and the columns have been exceeded, that means the job is done. It has to end the program. Okay. Otherwise, shift the pick point by -150, -30. Okay. That means it goes to the next one. So basically, it starts off from here. It checks the number of columns here, exceeded, so it comes here now. It shifted the row to the second row. And again went here, then went here, then here. And if everything has been completed, then it simply goes to end. Okay. So if both the columns and the rows have been exceeded, it simply goes to end and it stops the program there. Okay, so this was a very simple example of programming of a Puma 6 degree of freedom robot, which we will do in the lab. So you'll be looking at how to program the robot and what the robot is actually doing. Okay. We'll also look at cases where we can see the difference between move and moves command. Okay. Now, this is a very simple example which you can write a program by yourself. For example, this is a conveyor and parts are coming, so we can say that we have a sensor there, and sensor, if a part is there, it is 1, otherwise it is 0. Okay, and it communicates with the conveyor by means of a channel, maybe channel number 1, and the conveyor communicates with the robot in another channel, maybe channel number 2. Then the robot communicates with the conveyor in channel number 3. Okay, so you can write a very simple program with a logic that you can look at 0 1 0 1. So 0 1 0 1. Okay, so you can have 3 bits. Okay, so this is the sensor, this is the conveyor to the robot, and this is the robot to the conveyor. Okay, so for example, when a sensor part has come, it is saying the sensor part is 1, the other 2s are zeros. Okay, then the conveyor is telling the robot that a part has come, so the conveyor can become 1 and sensor is 0 and robot is 0 now. So depending on the logic, very often such things are done in PLCs in industries. Okay, the robot will pick up one, the object, put it here, take the next one with using some kind of indexing. Okay, so today we looked at very basic programming of a 6 degree of freedom Puma manipulator in VAL 2. So what we'll do is in the next class we'll be looking at the microcontroller, that is, how do you program a microcontroller, what are the various channels which are there on a microcontroller, and how do you do sensor interfacing, how do you control a servo motor, and then we'll move on to how do you control very simple planar manipulators, from which we'll move on to industrial robot programming. So industrial robot programming is done by for the Puma robot, so that's where we'll use whatever we studied today in our class. Okay, so we'll stop here today. Thank you.